Let's talk about discrete random variables. These have a few possible outcomes, finite number possible outcomes. So they could be very simple, just coin flip, outcome is heads or tails. Or if I roll a six-sided dice, the outcome is one of, well, 1, 2, 3, 4, 5, 6. I can make a list of the possible outcomes. Later we'll get to continuous distributions, where the possible outcomes might be, say, any real number. But in this case, there's a finite number of possible outcomes. We denote the expected value, e of x, as mu, a common use of that Greek letter to represent the mean. The mean, or expected value, of a discrete random variable is the sum of the probability of each of those occurrences times the value of x when that occurrence happens. That gives us the mean. It's exactly what you were doing back when you were a baby, figuring out the average of something. The variance is going to be the difference in the mean, the squared distance from the mean, times the probability of that particular thing occurring. Note that's variance, so the standard deviation is going to be the square root of that. Next, we have the rules of linear transformations, which work pretty much the way that we would like them to. If we have some variable x, which is a discrete random variable, and we want to create w as a times x plus b, then the mean of w is going to be a times the mean of b plus mean of x plus b, and the standard deviation of w is going to be a times the standard deviation of x. If I have two random variables, x and y, not necessarily independent, the two variables x and y are added to create z as the sum, then the mean of z is going to be the mean of x plus the mean of y. And the standard deviation of x is going to be the complicated formula, the square root of the variance of x plus the variance of y plus twice the covariance of x and y. If x and y are independent, then the covariance term is 0, so that just drops out. Sadly, these do not work for nonlinear transformation. If you've done a class in finance, you've probably often wished, hey, if only I had an easy formula for the mean of some stock return, and so many other formulas would be so much easier. But no, if it's e to the x, then those nice little formulas don't work. Or if I divided x and y, no easy formula. You can be grateful for the nice formulas we have, but don't get crazy and fooled into thinking that all the formulas are going to play nice. Nope, only the linear ones play nicely. So we look at some common discrete random variables that we often use. The uniform distribution comes up a lot. That's where there's the same probability of each outcome. Think about a six-sided dice. We'd like to believe that each side has the same probability of coming up. Probability of getting a 1 is the same probability of rolling a 6, the same as the probability of rolling a 4, etc. It's a basic assumption we'd like to make to play fair games. Now we'll work in class on how to modify that, discover how easy or difficult that may be, but we naturally state a null hypothesis for rolling dice to be the distribution should be uniform. Now there are lots of cases where I can specify the null hypothesis as saying that we would expect a uniform distribution of outcomes. There are cases where our intuition might be misleading. One of the classic cases is Benford's law, which basically states when we have measurements of a thing, then we're more likely to see leading values of like 1 or 2 than to see values of like 8 or 9. While you might think measurement should have a uniform distribution, it may not actually work out that way. We'll come back to that issue later. It gets complicated pretty quick, but another common discrete random variable we use is Bernoulli, which is where there's just one thing and either that thing happens or it doesn't happen. Just two outcomes. Something happens or not. Without loss of generality, we'll call the value when it happens to be 1 and the value when it doesn't happen to be 0. You can put in other values with a bit of linear transformation, those formulas we just reviewed, to calculate the mean and variance. If we have multiple Bernoulli trials, again, the formulas we just used for linear combinations. Probability of single occurrence happening is p, then the mean is p, and the standard deviation is the square root of p times 1 minus p. It's used for lots and lots of different events that have a yes or no answer, such as the data sets we're playing around with. Does a person have health insurance? That's yes or no. Do they live in a particular location? That's yes or no. Do they have some educational qualification? That's yes or no. With a bunch of Bernoulli trials, we get a binomial distribution, recording the sum of how many were 1, not 0. The mean of that is n times p. The standard deviation is the square root of n times p times 1 minus p. Again, those are easy to derive from the rules of linear combinations. The only tricky thing is sometimes people talk about the sum of the variables, how many are yes, or sometimes they talk about the fraction that are yes. For example, if I have 100 Bernoulli trials and 60 of them come up as successes, then I might record that as 60, or I might record that as 60% or 0.6. The math don't care. Either one works, which is sometimes why people might have one or the other inside their head, but sometimes not successful at communicating, getting what's inside the head to the outside world. You got to keep an eye on it. One of the common occurrences where we see binomial distributions used is looking at political polls. People say they'd vote for some candidate or support some issue or not. Define voting one way as success, voting the other way as a fail. It doesn't really necessarily matter which one you want, but then the plus or minus 2 percentage points that just, you hear about in all poll reporting, that just comes out of these formulas for linear combinations. In the notes, I go through that in a little more detail. You should make sure you understand that. Now, with a lot of Bernoulli trials, then those are going to form into coefficients given by Pascal's triangle. We can derive a formula that gives us, at the limit, as n goes to infinity, a normal distribution. We'll get into that later. Hold on to your seats.